Moving forward to exercise 22 or example 22 using the second fundamental theorem of calculus. Again, we're in section 4.4 of the book here. We want to find the derivative of f of x equals pi over 2 to x cubed of cosine of t dt. Notice we are in different variables, so what this means and what this is really asking us to do is take the derivative with respect to x of everything inside that integral. Okay, so we can kind of see the shortcut maybe a little bit, but it's going to change just slightly because it's an x cubed and not an x function, so we can't do the exact replacement, and I'll let you think about it at the end of the problem if you can see what is really going to happen when we use the second fundamental theorem of calculus. Okay, it does change a little bit because we're not starting at 0 and we have that x cubed here. So first step is still we're going to integrate. So we have pi over 2 to x cubed of cosine t dt. The antiderivative of cosine of t is sine of t. We're going to evaluate that from pi over 2 to x cubed. So we end up with sine of x cubed minus sine of pi over 2. Note, sine of pi over 2 is 1. So our function is actually sine of x cubed minus 1. Now we have to take the derivative of the function. Okay, and you're going to ask, well, how did we know we had to take the derivative? Well, in the beginning, what's given? We're given capital F of x equals this integrand. So we want to use and it tells us to use the second fundamental theorem of calculus. The second fundamental theorem of calculus tells us to take the derivative with respect to x of whatever that integrand is. So we've done the integral, and we've gotten sine of x cubed minus 1. Now we have to take the derivative of sine of x cubed minus 1. So you have to be careful. Remember, it's not sine cubed of x, it's sine of x cubed. So that's when we had to do u substitution and say u was x cubed, right? In that sort of scenario. Or we can recognize it's a chain rule, so the derivative of the inside times the derivative of the outside. If we take a look at that, so the derivative of sine of x cubed is going to be cosine of x cubed times the derivative of the inside stuff for the argument. The argument is x cubed, the derivative of x cubed is 3x squared, minus the derivative of 1, which is 0. So when we rewrite this so it makes a little bit more sense, it's 3x squared cosine of x cubed. Alright, so therefore, using the second fundamental theorem of calculus, we have to take the derivative of the integral with respect to x. Okay, we got 3x squared cosine of x cubed. Now, looking at this function, can you kind of see what happened? Where the shortcut might be, where we can drop and say cosine of x cubed, and then in the front we have to make sure that we're multiplying by 3x squared, which is the derivative of x cubed. So think about that as you work through the problems and things like that. This problem is beneficial for you on your homework problems 18, 19, and 20. So as you're working through those, make sure that you have this part of the notes handy for yourself. Okay? So let's look at example 23. We want to find the derivative of the integral, okay, given f of x equals negative 2 to x of t squared minus 2t dt. This is telling us to use the second fundamental theorem of calculus. How do I know that, right? Because it's giving us capital F of x here, and it's asking us to find the derivative of capital F of x. Remember, capital F of x tells us to take the integral, okay, of this function here. So it's the same thing. We're going to take the derivative with respect to x of the integral from negative 2 to x of t squared minus 2t dt. First step, antiderivative of t squared minus 2t is t cubed over 3 minus t squared. We're going to evaluate that from negative 2 to x. Alright, so this is nothing new. This is the same thing we've been doing. We're going to substitute x in to the antiderivative, and we're going to substitute negative 2 into the antiderivative. When we do that and we do all the algebra and simplify things down, we get x cubed over 3 minus x squared plus 4/3. Now, we've done the integral piece. We have to take the derivative of the integral. So now we're going to take the derivative of x cubed over 3 minus x squared plus 4/3. When we do that, we end up getting x squared minus 2x plus 0. So, what really happened there? If we take a look at the second fundamental theorem of calculus, we started with the derivative with respect to x of the integral from negative 2 to x of t squared minus 2t. Since it's negative 2 to x, we don't have to have that leading the derivative of x is what? Just 1. So we would have multiplied all that by 1. But notice that we could replace x where t is, and that's what we end up with. Okay, so that's the second fundamental theorem of calculus. Right here I could have just substituted it in and said that it's x squared minus 2x. So we replace x wherever t is. That works perfectly when we're going from something to x. Remember the previous example up here, example 22, we were going something to x cubed. So we did plug in the x cubed, but we had to make sure we multiplied by the derivative of x cubed, which was 3x squared. So there's where you just got to be careful, because anytime we're going something to x, the derivative of x is just 1. So there's really not as big of an impact here. Alright, let's look at example 24. This one's slightly different. This goes back to one of our principal integral functions. Okay? We're going from negative x to x of t cubed dt. In your head, you should automatically know what's going to happen here when you take the integral and we're going from negative x to x of t cubed. You can go through the painstaking process, or there was one of our properties, okay, that told us that that is equal to 0 back in 4.3. But if you forgot about that, just take the antiderivative, so it's t to the 4th over t. Evaluate that from negative x to x. It will work out to 0 for you, and then you have to take the derivative of 0, which is 0. So it still works out in the long run, even if you do the work and go through the painstaking process of doing it. Or if you could have remembered one of those properties that we did in 4.3, it would have been good. Alright, so these are going to apply to the your homework as well. I just want to roll through these a little bit, and then we'll wrap up for 4 notes wise. This is important because you'll have to do something like this in your physics class as well. So let's roll through example 5. We got some story problems, some real applications here of some integrals. So example 25. The force in newtons of a hydraulic cylinder in a press is proportional to the square of secant x, where x is the distance in meters that the cylinder is extended in its cycle. The domain of f is 0 to pi over 3, and f of 0 is 500. Well, now we got some initial conditions, and we have an interval that we have to go through. Alright, so part A asks us to find f as a function of x, and part B, find the average force exerted by the press over the interval. Well, average force means what? The average value theorem there that we're probably most likely going to apply, right, as we go through this. Alright, so this will help you on your homework assignment. In part A solution, we have to write that force is what? Some constant times secant squared x. That's coming from the verbiage up here. It's proportional to the square of secant x. That's where the secant squared x. Okay? And then we have to look at some f of 0, or k, or something is 500 here. So that's what's going to apply. Okay, so that's how we have to know that at our initial condition right there, that f of 0 is 500, that's telling us that k is 500. Okay, I know that's a little wordy to get that stuff out of, but the equation we're looking for in part A is f of x equals 500 secant squared x. So initially, right, we're at 500, and then in the words it says proportional to the square of secant x. That's where secant squared x comes into. Okay, so that's part A. Part B, we want to find the average force. So we need the average value integral, right? Remember, that's 1 over b minus a times the integral from a to b of f of x dx. So we know that what? Based on that interval, a is 0, b is pi over 3. So it's 1 over pi over 3 minus 0. And we're going to integrate from 0 to pi over 3 of 500 secant squared x. First thing I do, pull that 500 out in front of the integral. Okay, and on the bottom we have the pi over 3. Then let's just integrate that trig function. Okay, so we did some simplification there. Instead of leaving it as 500 over pi over 3, we multiply the numerator and the denominator by, 3 over pi. So the bottoms cancel out. We're left with 1500 over pi. Alright, and 0 to pi over 3 of secant squared dx. We know the antiderivative of secant squared x is tangent of x. Okay, and we're going to evaluate tangent of x from 0 to pi over 3. We're going to leave that coefficient of 1500 over pi out in front. That's going to multiply by as we evaluate the integral. So we're going to get tangent of pi over 3 minus tangent of 0. If you don't remember what tangent of pi over 3 is, or tangent of 0 is, use your calculator in radians form and get the value. So when you work that out, we're going to have 1500 over pi times the square root of 3 minus 0, or approximately 827 newtons. Okay, that's going to help you with problems 15 and 16 on your homework assignment. Okay, let's look at one more of these. Okay, we're going to look at volume. The volume liters of air in the lungs during a 5-second respiratory cycle is approximated by this given model. V equals 0.1729 T plus 0.1522 T squared minus 0.0374 T cubed. T is the time in seconds. Approximate the average volume of air in the lungs during one cycle. So anytime we're hearing the word average, we should use the average value function in this. Okay, no second fundamental theorem of calculus or anything like that in this one. Okay, but so we're going to substitute in, because if we read through the problem, okay, we want to approximate. Okay, using this model, and it says during one cycle, if we look in this first sentence, is 5 seconds. So A is 0, B is 5. So we have to do 1 over b minus a times the integral from a to b of f of t dt. So when we work through this, okay, we literally just have to find the antiderivative of each one of those functions, evaluate from 0 to 5, and multiply by 1/5. I think this problem is relatively easy. It's just kind of scary because of the wording. But if we can read through this and figure out that 5-second respiratory cycle, we want to approximate the average volume in air in the lungs during one cycle, we should know that that's from 0 to 5, and then just substitute into the average value theorem for the integral there. Okay, probably get roughly 0.53 liters. Okay, now net change, super easiest part of this entire homework assignment here. Alright, if we look at the net change, okay, that's the definite integral, the rate of change of a quantity f, capital F prime of x, gives the total change or net change in that quantity on the interval from a to b. So what are we really doing? It's super easy, super simple. The integral from a to b of the derivative of the integration. So that's why it's the derivative of capital F of x. The net change is literally us taking the antiderivative, evaluating it at b, minus the antiderivative, evaluating it a. Okay? So, important part for that, the net change of a function is always referred to as displacement. Okay? So that's when we start talking about displacement, or you get into physics, doing displacement and that sort of thing. Alright, so let's do an example. Last example for section 4.4, and then we will be done with it. This is example 27 in your notes on the website. Chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. Okay, and t is between 0 and 60 seconds. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay, so that's going to tell us how to set up our integral. We are just going to evaluate and literally just do the integral and get the net change. So 20 minutes from 0 to t of c prime of t dt is 0 to t of 180 plus 3t. So all we have to do is find the antiderivative of 180, which is 180t. Find the antiderivative of 3t, which is 3/2 t squared. Evaluate that from 0 to 20. So you're going to substitute in 20 and substitute in 0. You should approximately get 3,600 plus 600 equals 4,200 liters. So essentially, to find the net change, you are just going to evaluate the given integral. If you have any questions about this section, feel free to email me, and this ends everything for section 4.4. Next video we'll start section 5 or 4.5. Okay?